Section 6.4, polar coordinates. Up until now in math, in algebra and geometry, even in pre-calculus up to now, we have been graphing using the rectangular coordinate system. The rectangular coordinate system has an x and a y axis. We define points with an x and a y value. We graph things involving x's and y's. The polar coordinate system is another way of graphing, and it uses for its points an r and a theta. So the setup of the polar coordinate system involves a bunch of circles like this. And you still have an origin here in the middle, but instead of an x and a y axis, we just have a polar axis, which is at 0 degrees or 0 radians, if you think about your unit circle. Okay, and our unit circle is going to be very helpful for us graphing these things, because guess what? This theta is an angle. And just like with the unit circle and the trig stuff we've been doing, a positive theta, you're going to rotate around the positive direction, and negative theta, you'd rotate around the negative direction. The r is like a radius, kind of, that we are going to, once we graph our theta, or once we know where our theta is, we are going to go out so many lines. Whatever r is, that's how many lines we're going to go out to graph. So let's try that. Right here, we're going to graph these 3 points. So I want to graph 2 comma pi over 3. I drew in my origin here already, and so I want to start with the theta. I want to figure out where is pi over 3. You can use the unit circle to help you if you want to, but pi over 3 is going to be this line right here. And then I want to graph 2. And so I'm going to make each of these darker lines be 1. So like this is going to be 1, this is going to be 2. And so the point 2 comma pi over 3 is a distance of 2 from the origin on the line represented by pi over 3. Okay, so right here, 2 comma pi over 3. And so positive r's, you go the direction that you drew your line. Q here has negative 1 comma 3 pi over 4, so we're going to draw 3 pi over 4. 3 pi over 4, if you think about your unit circle or whatever, is right here. But I'm not going to go positive 1, which would be this direction. I'm going to go negative 1, which is the opposite direction. So you can kind of extend your line if you want to the other direction. Okay, that our negative values are going to be this direction instead of the direction we started with. And so a negative 1 is going to be right here. So this is negative 1 comma 3 pi over 4. Okay, so that's Q. So positive we would have put over here, but negative we need to extend our line the other direction and go the other direction. And then our last line here is 3 comma 225, and this is in degrees. So 225 degrees is, well, I didn't really mean to make it a dotted line. 225 degrees is right here, and then we just go out 3. So I would count 1, 2, 3, and that's where it is. So 3 comma 225. Okay, so those are those 3 points graphed out. Now, if they give you a point, there's only one place on this circle that that point can be. But if I think about the point like negative 1 comma 3 pi over 4, couldn't I have written that same point as if I went around my circle here, I started at 0 and I went around to this line? That would be an angle of 7 pi over 4. That's what this line is 7 pi over 4. And then if I'd used the angle 7 pi over 4, that would have made it a positive 1. Okay, or I could have used the negative, angle of this and written it a different way. So there's going to be an infinite number of ways you could write each of these points, and that brings us to the next slide. On this slide, the thing that you should pay attention to is, that's not what I wanted, this. Oh well, this right here, this is the important part of this slide, that if they give me r comma theta, I can plug it in to these two formulas, and that gives me any formula or any point that I want. So 3 comma pi over 3 is saying r is 3, theta is pi over 3. We're just going to fill that into these two formulas up here. So the first one has r, which is 3, comma, theta is pi over 3, plus 2n pi. 2n pi. Okay, or we could have negative r, so negative 3, comma, pi over 3 plus 2n plus 1 times pi. Okay, and these would be our two answers if they ask us to find all of the polar coordinates of a point. And it has to do with, like what we did with trig solutions, it has to do with the fact that I can go out 3 and I can go to pi over 3 and that's my point, or I can rotate around 2 pi and that angle in 3 gives me the same point. Or and I can do that over and over again. I can keep rotating around. And then the negative of that is a little bit more complicated of a formula, but you can just trust that that's true if you want to, or you can try and figure it out yourself why that's true. Coordinate conversion. So we're so used to using x's and y's, it's helpful to know how to go back and forth between them. So we can use these formulas basically that come from what we did in trig, that we used to actually have a formula that said like cosine theta equals x over r. So if you solve it for x, it's this. If you solve the similar equation for y, it's this. Tangent theta equals y over x, we've used that one recently. And then we had one that was the radius squared equals x squared plus y squared, which is a form of the Pythagorean theorem. These are the 4 formulas that are going to be really important for going back and forth between rectangular and polar coordinates and equations. So here we want to find the rectangular coordinates with the given polar coordinates. So I have an r and a theta, and I'm trying to go to x's and y's. And so I want to use the two formulas on the left here. This right here. We know that x will be whatever 3 cosine 5 pi over 6 is. Y will be 3 sine 5 pi over 6. And so we just need to figure out what those are. Now 5 pi over 6 is on our unit circle, so really we should probably be looking at our unit circle for this and getting exact values because those are the bestest. At 5 pi over 6, cosine is negative square root of 3 over 2. Okay, so I'm looking at my unit circle as we speak. X is 3 times cosine of 5 pi over 6. Cosine of 5 pi over 6 is negative square root of 3 over 2. And so x is really negative 3 square roots of 3 over 2. On y, I would have 3 times sine of 5 pi over 6, which is 1/2. Looking at my unit circle again, so y equals 3/2. So the point P as an x and a y is negative 3 square roots of 3 over 2, comma 3/2. Okay, and then Q, I will have to use my calculator for because you may or may not know this, but negative 200 is not on the unit circle. But we're going to use the same formulas. So 2 cosine negative 200 degrees and 2 sine negative 200 degrees. So make sure that your calculator is in degree mode for that. That gives me for x negative 1.88 and for y 0.68. So this point would be negative 1.88 comma 0.68. That would be my answer. So to convert from polar to rectangular, you just use the two on the left. So we're going to use the 2 on the right to convert from rectangular to polar coordinates. So those two formulas were r squared equals x squared plus y squared, and then tangent theta equals y over x. So the point -1 comma 1 is in the second quadrant over here, and that's going to matter because we're going to have to use inverse tangent, and so we need to make sure that we know what quadrant we're supposed to be in. R squared equals x squared plus y squared. So r squared equals 2, which means r equals the square root of 2. The inverse tangent of our y value over our x value, and actually this is going to be something that's on the unit circle. The inverse tangent of 1, or tangent theta equals 1, what is theta, is basically what we're asking. And we want the answer that's in the second quadrant, so that was helpful that I drew that. That's going to happen at 3 pi over 4, because the only way I can get tangent to be 1 is if my x and my y values are the same, or they could be, opposite signs from each other, which is the case in this one. Sorry, that should have been -1. So, but theta is 3 pi over 4, so this is the point square root of 2 comma 3 pi over 4. Let's look here at Q. If I want to find my r coordinate, I do -3 squared plus 0 squared, which is 9, and then I square root it to get r is 3. And if you could have come up with that sooner, then that's fine. And then again, if we look at where this is, if I graph -3 comma 0, I get a point right here. What angle is that? That's going to be an angle of pi. I was about to say pi over 2, but it's not. It's pi. So this is the point 3 comma pi. But if we didn't know that, we could have done the inverse tangent of 0 over -3. And it should have, told us that it was 3.14 if we put it in our calculator. Or if we had said, okay, where's tangent 0 on our unit circle, hopefully would have gotten there. So 3 comma pi. Equation conversion. So there is basically tricks to this, that we are looking for a way to get these equations in the middle here to appear so that we can replace, basically. And so if we have cosines here, so we're trying to get to rectangular coordinates, it'd be really great if we had things like r squared, because then we could replace it with x squared plus y squared. It'd be really great if we had r cosine theta, because that equals x. And it'd be really great if we had r sine theta, which is y. There's something we're allowed to do with polar coordinates that are in the polar coordinate system that we're not allowed to do in the rectangular coordinate system. And on this first one, what we're going to do is multiply both sides by r. And it is not going to actually do anything weird if we times both of these by r, both sides, like it would if we were in the rectangular coordinate system. Okay, because we times both sides by r, look at the two things that appeared here. I have r squared, which I can change to be x squared plus y squared. And then I have 4r cosine theta, so the 4 is going to stay there, but r cosine theta is going to change to x. And then in the book, it asks us also to look at this graph. And so I would move everything to one side here to think about this graph, and I would actually complete the square on the x's here. This is a circle formula. Okay, if I complete the square here, I divide by 2 and get -2, and I square that and I get a +4 that I add to both sides. This is x minus 2 squared plus y squared equals 4. So this is a circle centered at 2, 0 , with a radius of 2. And that has to do with, this is a circle formula here that is centered at the opposite of this negative 2 is 2. There isn't anything affecting y, so our y value is 0. This is our radius squared, this 4. So our radius is the square root of what this is. Okay, and then we could draw this if we wanted to as well. On this second one, r equals 4 secant theta, I would divide both sides by secant, because it'd be great if I had you know, an R over here or whatever, and I might could change it somehow to like cosine, but let's see what happens. Let's divide by secant on both sides. So we have R, and isn't secant on the bottom the same as having cosine on the top? And isn't r cosine theta according to this equal to x? So this equation, r equals 4 secant theta, is the same as the equation x equals 4, which is a vertical line at x equals 4. Now let's go the other direction. One way that we could do this is we could go ahead and replace x with r cosine theta and y with r sine theta, but we're trying to get like it solved to r with r by itself, and that would be a lot of that would be a lot harder to work through it if we change it first. So before we do anything, let's go ahead and square both of these. So this is x minus 3 times x minus 3, and y minus 2 times y minus 2. And so that would be x squared minus 6x plus 9. And this would be y squared minus 4y plus 4 equals 13. Let's add 9 and 4 is 13, right? And then I have a 13 on the other side that I could subtract over, so that will cancel out all my numbers, right? And so let's rewrite this as x squared plus y squared minus 6x minus 4y. All my numbers are gone, so the right side equals 0. Now, this right here, x squared plus y squared, hey, that's the same thing as r squared. And I can put in for x r cosine theta, so negative 6 r cosine theta minus 4 y is r sine theta. It equals 0. And now, again, something I can do in the polar coordinate system that I can't do in the rectangular coordinate system is I can basically factor out an r and then just get rid of it. Okay, so that r, just like earlier we multiplied everything by r, well, I can divide by r and get rid of it, and it's gone. And then I just have to add the 6 cosine theta and the 4 sine theta over to the other side to solve this for r. And then I can put this into my calculator. If we want to put things into our calculator in polar coordinates, if you go to mode, there is a line that says FUNCPAR. That's not a P. PAR, and then POL. That's we want POL for polar, and then you'll switch between degree and radian depending on what you're doing in a problem. But if I wanted to graph this, I could stick it in to polar with radian mode, and it would show me what this looks like. This is a circle, just like the last one would have been. So then we have kind of an application problem here that basically, if we are looking on a radar, they actually use polar coordinates on radars and like airplanes and stuff, and so we can use the law of cosines, basically a form of the law of cosines. So let's call this r1 and theta 1 and r2 and theta 2. Okay, so this is going to be r1 squared plus r2 squared minus 2 times r1, r2, and then cosine of our angles subtracted. And it doesn't really matter which order that we subtract our angles in. So we're trying to find what the distance, which is d, is. So 8 squared plus 5 squared minus 2 times 8 times 5 cosine 110 minus 15. And then you just put it in your calculator and see what you get. Make sure you are in degree mode to do this. So for d squared, I got 95.97, and then we square root each side, which I did not actually successfully do. Okay, d equals 9.8 miles. And that's the answer. So that is section 6.4.